Okay, so today, what I wanted to do is to talk about searching for scaling and I'm going to talk about two different places where we've searched. One is in animal behavior, and the other is in embryonic development. And you'll see what we mean by scaling in these two different cases is a little bit different, but I hope you'll get some sense for the spirit of what we're trying to do. So let's start with the example of fly behavior. And on Tuesday, I showed you how we now have, our experimentalist friends can now take a very high resolution movie, high spatial resolution, high temporal resolution movie of a fly walking around, doing whatever it wants to do in a featureless arena, so it's not being driven by anything. And you can take those data, so you start with a movie, and what you end up with is a time series, SI of t, which you can think of as saying, well, SI of t is 1 if you're in behavioral state I at time t, and 0 otherwise. And you'll remember that I runs up to some number of states, which is about 100. And time, I can think of measuring time either in frames of the movie, which are 1/100th of a second, or sometimes it's useful to think about time as being measured by transitions between states. So not what is not, t plus 1 is not a fixed amount of time in the future, it's the next thing that the fly is doing. And one reason you might want to do this is that there's a whole literature about the amount of time animals spend doing one thing. And that's complicated, and I actually don't think it's to the point that we want to get at, because if there's scaling, that's something that happens on long time scales, right? And so somehow the fact that the amount of time you spend doing one thing varies, maybe that's not so interesting. So I'm going to show you one thing where we count time in transitions, and then I'll show you another thing where we count time in seconds. And you can decide. So how do you measure correlations in a system like this? We're used to measuring correlations so for example, if I have discrete states, you think about an Ising model, there are 2 states, I know how to measure the spin-spin correlation function, but what if I have 100 states? So in principle, at each time delay, there's a correlation matrix, which you can think of as the probability that I'm in state I at time t, given that I was in state j at time 0. That's a very complicated object, and we can say some things about that, but then I would certainly need the slides, because it's a 100 by 100 matrix at each time, and I'm not going to try and draw that. But there's a much simpler thing you can ask, which is the coincidence probability as a function of delay tau. And what this is the average let me just say it in words. It's the probability that SI of t is SI of t plus tau. So what you're asking is not what's the conditional probability of being in one state given that you used to be in another state? Just, did you come back to the same state? And actually, since I'm not really interested in what flies do, right? He's grooming, he's walking, he's scratching himself. I don't care. So I'm going to sum over all the states, right? Just ask, did you come back to the same state or not as a measure of correlation? And if you measure tau in transitions, and you measure the log of PC, and you do this on a log scale, you find something that, by the way, is not a particularly good power law, so that's not going to be the, that's not going to be the thing we're interested in. But what you could also do is to say, I can measure the transition probabilities from one state to the next, right? I have enough data to do that. And if the transitions were Markovian, so that what the transition you make depends on where you are now, but not where you are before, then I can compute this probability just by multiplying the transition matrices again and again. And I'd get this. And the scale here is that this is about 30 transitions, and this is 1,000 transitions. So if the fly were transitioning from one state to the next in a Markovian way without some internal memory, then, well, you wouldn't forget where you are after one state because there's some, I mean, so, you know, you could imagine, for example, that one possibility is when I'm in state 1, I always transition to state 2, and when I'm in state 2, I transition to state 3, and so on. And I do that in perfect order. And then actually, I come back to the same state exactly after 100 times, 100 time steps, or 100 transitions. And I do it again at 200, and I do it again at 300. And so I can have structure on long timescales that comes from a Markovian rule, but not from the actual transition probabilities, right? The actual transition probabilities have the property that if the fly didn't keep some memory, it would not revisit the same state. And that it would forget what state it was in after about 30 transitions. But in fact, there's still an easily observable memory after 1,000 transitions. And I'll remind you that we're only asking about the coincidence probability. There could be subtler forms of memory, which you can see if you look at these big matrices. So this is a hint that there are correlations that last over long timescales, and it's natural to ask whether there's any sign that those correlations are scale invariant. It's not clear what correlations you should compute, and so on. So one of the things we tried, you will not be surprised to learn, is to build a maximum entropy model of the sequence of states. But if you think about it, that's not going to work. Because since there are 100 states, if I want to match the correlation function, as I said, is a 100 by 100 matrix at each value of the time delay. And so if I want to match the correlations across hundreds of transitions, I need hundreds of 100 by 100 matrices, and very quickly I'll run out of data. So we decided to do something relatively crude. We said, let's take SI, where I runs from 1 to something like 100, and map it into sigma, which is just plus or minus 1. So what we're doing is we're taking the 100 states and we're putting them into 2 groups. And we'll just keep track of which group we're in. So which group, how should you do the grouping? Well, you're interested in temporal correlations. So here's my grouping. And I want to maximize by choosing different groupings, the information between sigma at t and sigma at t plus 1. So I'm saying that I can't keep track of all 100 states and do what I want to do, so I'm going to collapse down to a two-state description, but I want to do that in a way that keeps as much of the temporal correlation as I possibly can. And by the way, since these are binary variables, mutual information is sort of overkill. You could just compute correlations. But conception, I mean, we didn't know for sure we were only going to do binary, so we sort of set the problem up thinking about the information. So in this case, for this discussion, this is the next state. Or alternatively, after one transition. So you're counting time, you're letting the fly tell you how to count time. You switched microscopic states. Yes, sorry. Right. If we had done that, if we'd done that here, then it would have, then we just alternate, right? So yeah, so it's transitions in the full 100 state rich description. Okay. So what that means, of course, is that your binary states will be groupings of states that you tend to wander around in for a while before jumping away to something else. And they make sense. Roughly speaking, one of the two states is do things fast, and the other one is do things slowly. Okay. So if you're doing things slowly, you might do something different, but you keep doing it slowly. Not surprising. Okay. Nothing interesting has happened yet. So how do I want to build a maximum entropy model? I want to match the average state, right? Or alternatively, the probability of being in one state versus the other. And I want to match so this you can think of as being the magnetization, and this you can think of as being the correlation function. Of course, you should subtract m squared to get a correlation. Okay. So what is the maximum entropy model that does this? Well, the maximum entropy model that does this, right, the variables are Ising spins that live along a line, and the line is time, and the lattice spacing is transitions. And in order to be sure I get the magnetization right, I have to apply a magnetic field. In order to make sure I get the pairwise correlations right, I have to allow the spins to interact with each other as a function of their distance along the line. Okay. So it's an Ising spin chain. And we know a lot about different Ising spin chains. But the question is, which Ising spin chain is it? That is to say, when you fit the correlation function, when you match the correlation function, what does J turn out to be? So you have to tell me how much of the correlation function you're going to match. So let's say I can go out to about 1,000 transitions. If you match a few, you go out to a few dozen transitions, then you get something for J that looks kind of like this, and then it sort of turns up at the end. So what's happening? Correlations, of course, decay pretty much monotonically. I mean, they don't have to, but they do. So why doesn't the interaction decay monotonically? Well, the answer is that you've decided to only match the correlations over some fixed window. But in order to produce those correlations, the sort of the last guy has to interact a little bit more, because really there are interactions that extend much further that you're not keeping track of. So to make up for that, you have to pile them up. So if you match a wider range of the correlation function, then you see that. And if you match a wider range of the correlation function, you see that. And if you match as much as you have data, you see that with amazing accuracy, and I say amazing because it just comes out of the data, right? I mean, we don't have a theory of anything. We're just letting the machinery run. What comes out is that the interaction between spins at distance separated by tau transitions is proportional to 1 over the square of the distance. So some of you will know that the Ising model in one dimension with interactions that are 1 over the square of the distance is a very special model. Not only is it a special model in the space of models, it's also a special model in the history of the development of the subject. You know that nearest neighbor interactions in one dimension can't produce ordering, so there's no phase transition. If you let the interactions extend over longer and longer ranges, eventually something happens. And if the interactions decay very slowly, then unless you do something to rescale the strength of the interaction with the size of the system, you'll end up with the energy not being extensive. This is the borderline case. And so it has a phase transition. In fact, it's a phase transition in the same universality class as the XY model. It's the BT transition. The same problem arises in the analysis of the Kondo model in condensed matter physics. So it played this very important historical role, sort of circa, I mean, the mathematical physicists knew it was special long before, but it played this very important role in the development of renormalization group ideas in the sort of circa 1970. In fact, there was sort of an RG calculation for the inverse square model, Ising model, before there was a full-blown RG. So, that's all footnote, right? But it's an interesting footnote because why on earth is it that when you analyze trajectories of animal behavior, this is the model that pops out? It's a complete surprise. So you might say, well, that's the model that pops out, but how do you know that it's a good model? Well, we can do the same kind of thing we did yesterday, I think, which is, for example, what this predicts, of course, is that whether the spin at this time wants to be up or down depends on the effective field that's contributed by all of the spins in the past. So I can compute what that is, and in fact, just to be sure that I'm not, there are some little wiggles in here. They really are very small. But just to be sure that it's not working because we put all the wiggles in the right place and are overfitting, let's just assume that the interaction is 1 over tau squared. And the only parameter we're allowed to adjust is A. Then we can try and compute the effective field and ask whether that correctly predicts the probability of the spin being up or down, and it matches perfectly over the full dynamic range of fields that you access. Another interesting thing, which I think is a reminder about the analysis of animal behavior, is something that's completely obvious from the point of view of statistical mechanics, but we don't always think about it in the context of animal behavior. And that is that the magnetization is not 0. there's a bias between the two states. In fact, the bias is, I think the average magnetization is like 0.46 or something, which means that if you were just thinking about the bias as being a magnetic field, it would be a number of order 1. But because there are interactions that extend over very long distances in time, the actual magnetic field that goes here is less than 10 to the minus 2. So again, you know this, right? If you have a magnet and you're in a regime where there are strong correlations, if you apply a small magnetic field, you can get a very big response. In the extreme, at an actual critical point, as Mauro pointed out, you can have non-analytic responses, right? So you basically have an infinite susceptibility. So what this means is that the intrinsic bias between the states is actually quite small, and the apparent bias is very large because the bias is applied every time you choose a new state, but there are interactions that keep you in the same state. And so that amplifies your intrinsic bias. So this was our first hint that there's something going on here which is scale invariant, which is the fact that if I ask you about the effective interactions or the direct statistical dependencies between states at different times, there's no characteristic scale over which that decays. Okay? Yeah. So I said that this is a hint that there's something scale invariant going on underneath all this behavior, because if I ask you to build a model of how states depend on each other as a function of their temporal separation, there is no characteristic scale on which that dependency decays. Just decays as a power of the distance. Okay. So this is, so I think if you've been, one way of thinking about what's going on both in the lectures that Mauro is giving and that I'm giving is that we kind of go back and forth between building models and viewing the data through the lens of the model, and maybe there's an interesting conclusion about something being critical or something being scale invariant or whatever, but then there's also the question of whether you can look directly at the data. So we'd like to look, so this is interesting, and maybe we should have done more with it. We sort of left it sitting there. But what we decided, what we really wanted to do was to look much more directly at the data. So how am I going to do this? I have this problem that, can we look directly at the data? So as I say, you could think about just measuring correlation functions. So, for example, you could measure a correlation function as a function of tau, which is Si at t, Si at t plus tau. And you would average this. But then since you want a correlation function, you should have subtracted the means. So you have to subtract Si of t, Si of t. This, you'll notice, is the probability that you're in state I at both times t and t plus tau. So if I sum up over I, then this is what I've called PC of tau, the probability of being in the same state. And this is a sort of subtracting off what you would get if the two times were completely independent of each other, right? So it's a kind of connected version of this coincidence probability. So good, I have a correlation function. Plot it, see if it's scale invariant. Problem, where do you get the averages? So one possibility is to say, well, they do these experiments for an hour. So let's compute the average over the whole hour. But what that means is that there can't be any variance on the scale of an hour, because you defined the mean to be the mean over the hour. And so, since there can't be any variance on the scale of an hour, the correlation function has to go negative in order to, right, the variance over a window is the integral of the correlation function. Sorry. Let me stop for a moment. The problem that I'm worried about is related to a problem that you all know, and that's the problem of diffusion. So if you watch a Brownian particle, you could say, well, the fundamental quantity is the autocorrelation function of the velocity. But that decays on a very short timescale. So, you know, with fancy modern techniques, maybe you can measure it, but there's something much simpler you could do, which is to measure the double integral of the correlation function, which is the mean squared displacement. Because that just grows with time, and if you wait longer, it gets bigger and bigger, and you can literally see it more easily. Right? So it's an old idea that by somehow integrating your variables in the right way, you can get measures of correlation that are easier to access. And for example, the fact that the correlations of velocity are short-ranged in time is why you get diffusion with the mean square displacement growing linearly in time, because there's no other scale coming from the correlation function itself. If for some reason the correlation function had long tails, then you would grow not as an integer power with 1, but as some fractional power that's related to the fractional power of the decay of the velocity correlations, which is called anomalous diffusion. So you have this idea that variances of things are related to integrals of correlation functions. But if I define the mean to be the mean over my data on a 1-hour timescale, then that means that there is no variance of the average over 1 hour, because it's the average, right? And since variances are integrals of correlation functions, you force the correlation function to go negative, whether it wanted to or not, right? Whether it's intrinsically crossing over or not. Is this making sense? So what you can do as an exercise is to ask yourself, suppose that you have a process that has correlations that decay on some characteristic scale tau sub c, and you decide that you're going to define the mean by averaging over a window of size capital T, what correlation function would you actually measure? And the answer is that if the correlation time is very short compared to the observation time capital T, you'll see the exponential decay of correlations, and there'll be a little tiny negative piece that lasts a long time that you probably won't even see in your data because of error bars. But if the correlation time gets to be comparable to the window of your observation, now you're really in trouble, and you've distorted the correlation function. And if the intrinsic correlation function is a power law, you can very quickly convince yourself that you will almost never see a clean power law. Essentially because you never really have independent samples to average over, right? So subtracting the mean becomes problematic. And you say, okay, let me talk to my friends who study animal behavior. Nobody studies the behavior of one animal. They always study many animals. And they average over them. So let's choose as the thing we're going to pick the average, not over time, but over the many different flies that we're going to run through the rig. The problem with that is that that only makes sense if all the flies do the same thing. And if they have individual differences, which is something that we imagine animals have, us included, of course, but even flies, perhaps, then the thing that we're subtracting off isn't quite the right thing. Right? In particular, if you subtract off the mean across individuals, and you let tau go to infinity, then what this will give you is the variance over individuals. It won't decay to zero. And one way of thinking about that is so what that means phenomenologically is that if you use an average over individuals, you've conflated individual differences with long-time correlations. And that's for a very simple reason. You have an infinitely long memory of your own identity, right? So because you've treated everybody as being the same, you've confounded being correlated in time with being yourself and being different from the other guy in the average. Okay, I'm waving my hands about this just because you can write down lots of equations, but they just say what I said in words, right? It's worth doing to understand what's going on, but I don't want to belabor the point too much. But so is this clear that there's a problem here of what to subtract? Which, by the way, just usually doesn't come up in our traditional physics examples because of the scale of the experiments, the scale of the correlations, and so on, right? It's a regime that you don't usually have to worry about. Our friends who work on collective animal behavior do have to worry about this. So for instance, in analyzing the fluctuations of velocities of birds in a flock, you have to ask, well, what was the average? You don't want the average over the lifetime of the bird because presumably, on average, she doesn't go in any particular direction. And to get a sense about ordering, you want the average over the flock right now. But then now, if I take that again forces correlation functions to go negative, and so you have to be very careful in your analysis. So there's a problem that's come up a few times, and as far as I know, it doesn't come up in traditional physics context, but does come up when you try to use the same apparatus to think, the same mathematical apparatus to think about biological systems. So what we decided to try was to go directly at this. And I'm going to write things as if time were continuous, but it does come in discrete time steps of the video frames. So here we're going to use real time, not transitions. So if I ask you, if I have many flies that I got to look at, I can define an SI of t for each individual. And then for each individual, I can say, let me look at a window of size capital T. And that quantity, so if I average SI alpha of t, that's the estimate, that's an estimate of the probability of being in state I that I got from fly alpha in windows of size t. So I can't assume that measurements at different times are independent of each other, because there might be long-range correlations. But when one fly has finished spending his or her hour in the apparatus and you take them out and you put another one in, presumably your observations on the two different flies are independent of each other. So it makes sense to ask about the variance of this. That is to say, you should I average over all the flies. I subtract that from the estimate that I got from each individual fly. I square and I average that over the flies. That's the variance in my estimate across individuals. And then I say, well, once again, I don't really care what flies are doing, so I'm not interested in which state we're talking about, so I should sum over all the states. And let me call that quantity phi 2 of t. So what do I expect? What I expect is that if I have short-range correlations, then phi 2 as t goes to infinity should look something like a over t plus b, where this comes from individual differences. And this comes from the fact that as I increase the size of my window, I get a better and better estimate of what the probability is. And if the correlations are short-ranged, then I have a number of independent measurements which is proportional to the size of my window, and my variance of an estimate goes, or the errors in my estimate go as 1 over the square root of the number of samples. And so since I'm talking about a variance, it's 1 over the number of samples, which is t. Okay? If instead there are underlying long-ranged correlations, so that if you could really get directly at the correlation functions, right, that are sitting in here, you would see some sort of power law decay. Then you should see well, I'm going to be pedantic. I should see decay as some power which is not trivial, right? So let's ask what happens. Okay, is this clear? Yeah.
Say me again. Actually, I didn't understand because I didn't hear it very well, and also can't read very well.
Oh, sorry.
No,
my handwriting is decaying with time. Okay.
No, this it's called short range
yeah,
correlation.
so
That's the short range.
Maybe the way to say it is, if I have a finite correlation time, right? So there's some characteristic time which is short compared to my observation time. If I have a finite correlation time, then if I make measurements over times that are much longer than the correlation time, then my estimate of the probability should improve because the number of samples I'm collecting is proportional to the amount of time that I'm observing. So that gives me this behavior. And then there's the problem that I'm computing a variance across individuals, and that might not be 0. So I'm going to get if I go to very long windows, all of my statistical errors, all of the variance that comes from statistics will go away, and I'll be left only with real variance across the individuals. On the other hand, if I have long-range correlations, so if S of t plus tau, and you take the connected part, somehow goes like 1 over tau to the 2 delta, then I should see this. Okay. And the reason you don't have to correct the exponent is because although you're taking an integral, you're doing it as an average, so you don't change dimensions.
Okay,
good?
Thank you.
Okay, so that's the idea. So let's just try it and look at the data. So you know, you've seen a lot of log-log plots. But nobody tells you when you're starting that you should use a log-log plot. And in fact, you might think that, this is a pretty fast decay, so if I make a linear plot, I'll see something go to a plateau and it'll be very nice. And indeed, if you look on a time scale of several seconds, you see something that decays and looks like it's starting to plateau, but B is quite large. So you say, okay, there are correlations on the time scale of a few seconds, and there's lots of individual differences. That wouldn't surprise most people. So then you say, well, I have an hour's worth of data, so let me extend out to minutes instead of a few seconds. And now my dynamic range of this quantity phi becomes larger, so let me use a semi-log plot. And now the same thing happens, but of course on a longer time scale. And now you finally realize, okay, right. Did something just, no, it's okay, good. And so let me tell you what happens on the log-log plot. So I'm going to take the logarithm of phi 2 versus the logarithm of tau. And here's 1 second. And here's 10 to the 3 seconds. I'll remind you that an hour is 3 times 10 to the 3 seconds. So 3.6. And what you see, and I'll give you one example of the error bars, right? The error bars are about this big. And you see something that looks, there's just a beginning, it's mostly a straight line, and there's a little bit of curvature at the end. So you start to think, maybe this is right. Maybe it really is scale invariant. Maybe I am seeing a power law decay. So you fit this to your data, and you subtract your estimate of B. And now you have an almost perfect power law over 3 decades. The line that you draw goes through all of the error bars, right? And delta is 0.180 plus or minus 0.004. Right? The error bars are so small that you can define an exponent to its second or third decimal place, depending on how you think about it. Over 3 decades. Footnote, B is actually not very large. So remember how I told you that if you average over individuals, individual differences can look like long-range correlations. But it also works the other way. If you and I start doing something, and we're intrinsically different from each other, then if you measure the variance of our behavior over long times, you'll get a non-zero answer. But suppose that we are statistically the same, but we just happen to start in a different place. Then because our correlations extend over very long times, we never quite forget where we started over the course of the experiment. And so that means you'll think that we're intrinsically different, but it's just that we're 2 finite samples out of the same distribution. So in the presence of long-range correlations, you will generally, in any finite experiment, unless you think very carefully about it, you will overestimate the scale of individual differences, which is really interesting because the biologists are always tormenting us with individual differences, and this way we can make them smaller, legitimately, right? We're explaining the structure of the correlations, and in that structure, you have this confusion. And so the actual variance across individuals that we estimate is nearly an order of magnitude smaller than the variance that you actually measure on the 1-hour timescale. Okay. So that's interesting. this is one of those, you see a power law, what do you think? So the first thing I want to remind you of is that you can get a power law in time by having decays that are on different timescales. And formally, to get a power law, you need a continuous distribution of timescales. But in practice with finite data, you just need a bunch of timescales that are spread out enough. But in fact, in these data, you can produce something whose fit to the data is as good as this is with 6 different timescales, each timescale being defined as a component of the correlations that decay exponentially. But what you'll find is that because the data is so tight around the power law, the magnitude of the contribution from each component has to be precisely tuned to its timescale. So you've really just transferred so you could say, don't be impressed by power law decays in time, because that's just because there's a lot of exponential decays on different timescales. But actually, to fit these data, you need the amplitudes of each of those decays to be precisely tied to their timescale. So you've just transferred the problem, right? You could say, well, it's not that the system's intrinsically scale invariant, there's 6 different timescales, except that the magnitude of the fluctuations on each timescale is a very precise function of the timescale itself. So that path is sort of complicated, right? It's always true if you think about computing, I don't know, the spin-spin correlation function as a function of time in a magnet. You know that you can think about that in terms, you can Fourier transform in space. The spin-spin correlation function at a point is a sum over terms that come from each of the Fourier components. Each of the Fourier components is decaying at its own rate, and then together they make whatever it is you see. So the idea that you can decompose even genuinely critical fluctuations into a sum of exponentials is not surprising. That's sort of always how it works. Those are the normal modes of the system, right? Or the elementary excitations. And so it's always going to be true that when you see a power law, even if that you could always reinterpret that as saying, well, what I have is some big dynamical system that's got lots of modes, and the density of decay rates of those modes is such that it comes out looking like a power law. So can you do any better than this? So some of you will know that in thinking about critical phenomena, you don't need to do it, but you can also think about the effective field theory that describes the system and it is conformally invariant at the critical point. And when you have conformal invariance, you can relate correlations functions of different orders to one another. So this is a very simple problem because I just have one dimension of time, right? So what's the prediction in the spirit of conformal field theory? The prediction is that if instead of looking at the second power, I looked at the third power, let me put the equal sign over here. Right, everything's the same, but instead I look at the third, not the variance of my estimate around its mean, but the third power of the fluctuations around the mean. You might expect that phi 3 would go like A3 over T to the 3 delta plus B3. So you plot phi 3, you fit to this form. Of course, you don't insist that it's 3 delta, you just insist that it's a power, you just try out a power. The error bars are a bit bigger. But it works, and the delta that you get from measuring the third moment is the delta that you measure from measuring the second moment, again, with an error which is less than 0.01. So it's not only that something related to pairwise correlations decays as if there were some underlying thing whose time was t to the delta, but the higher moments do this too. We tried the fourth moment, but the data really aren't good enough to get a reliable answer. Let me do one more thing, which is to point out that you know that when you're looking for long-range correlations, they're supposed to be universal. So that means that if you change what you're doing on the short time scale, it shouldn't matter. So I define states by looking at one moment in time, and I have 100 of them. Suppose I define states by looking at two successive moments in time and ask, what pair of states do you occupy? Well, you might worry that there's 10,000 of those and I'm going to run out of data, but it turns out that only 1,000 of them are ever visited, and I have just enough data to do that. So I can redefine state to be the state in two successive frames instead of one frame. And then I can do the same exercise. And what am I supposed to get? Well, I'll get a different amplitude and a different background, but the exponent should still be 2 delta, right? Because it's still a 2-point function. Or alternatively, if you really want to be formal about it, it's a 4-point function, but of the 4 times, 2 of them are close together and therefore drop out of the problem, and it's only the 1 time that's left. So you should see the same exponent, and you do with the same accuracy. So what we think is that we've seen signatures of scale invariant correlations in the behavior of the fly that pass multiple tests for scale invariance. So we have multiple ways of measuring the same underlying exponent that agree with each other in the second decimal place. And the observation of scaling is across 3 decades in time. And because the experiment is an hour long, and if you go back and think about how we define states, we look at little snippets of behavior which are of order a second long, we really only have 3 decades of data. So you couldn't see, in this experiment, you couldn't see more than this, and you see all of it, okay? As a footnote, the primordial example of, it's not an example in the sense that we know for sure that it's true, but it's a motivating example for scale invariance in behavior is language, right? You have structure on the scale of phonemes, which becomes structure on the scale of syllables, which becomes structure on the scale of words, phrases, sentences, paragraphs, ideas, right? And there's an old sort of, I mean, to call it a controversy might be overstating it. There are sort of disconnected literatures of people who emphasize the fact that it's on all scales and therefore things should be scale invariant versus the people who have a very strict hierarchical view and different things are happening on the different scales and so on. One of the motivating observations for part of the, you will not be surprised to learn that physicists are much more enamored of the idea that it's scale invariant than linguists are. Remember, linguists spend more time thinking about it, so maybe we should actually take that seriously, but never mind. One of the pieces of evidence that kind of triggered interest in the physics community was this beautiful experiment that Shannon did just a few years after the introduction of information theory. He showed people n letters in sequence and asked them to guess the next letter. And he showed that by looking at the number of times they needed in order to get it right, and the distribution over that, you could put a bound on the entropy of one letter given the previous n letters. Essentially, you're using the person as an encoder. And so you can look at the entropy of their responses, and that tells you about the conditional entropy of the letters. And he thought he saw something that decayed to some plateau after at n equals 100. In fairness, he jumped from something like 10 to something like 100, and there was a drop, but he sort of sketched a plateau. I mean, you know, this is 1952, right? And also, the genius of doing an experiment with people to get a bound on the entropy of English. And it's, okay. You may know that the way you train a large language model is to train it to predict the next token, but the next thing in the sequence. So in fact, the way you train a large language model is to train it to play Shannon's guessing game. The difference is that while I can ask you to guess the next letter, it's hard to ask you for your estimate of the probability distribution. In particular, it's hard to get many decimal places out of you when you tell me what you think. But with the large language model, you can do that. The language model returns you can not only ask it to return its best guess, you can ask it to return the distribution. And using that, you can again put a bound on the entropy of the actual text that you're talking about. It's not only a property of the model, it's a property of the text itself. And for many families of texts, what you now see is that the conditional entropy is decaying as a very slow power of the length of the history out to thousands of tokens. So maybe we can sort of resurrect the idea of scale invariance in language, although it's a complicated story and people are just getting started with it. So it's in the same spirit. Okay. I have half an hour to tell you about embryos. I think I can do that, but I should pause here and see if there's something on people's minds. Yes?
The 1D inverse square Ising model is one of these models that has the strange property that there's at low temperature, there's a continuum of critical exponents.
Yes.
So you wouldn't normally expect universality from things in that class at low temperature, because if you changed small details of the situation, like the individual or the environment they're in, that you expect that exponents continually change. So why do you have such a robust scaling here if it's supposed to be coming from an inverse square Ising?
The connection between the two blackboards is very loose.
Sure. I accept that. Yeah.
No, I mean, you know, we tried this, and we thought it was kind of cool. The referees weren't as impressed. Maybe they were right. I mean, after all, you've taken the real behavior and collapsed it into two states. You chose some way of doing that. I mean, we think it's a rational choice, but it's not unique. A whole bunch of stuff happened here. The fact that it's so accurately the inverse square Ising model is surprising, but who knows? When you look at the data, you're looking at the data. So what you could say is, this is not a bad phenomenological summary, but it doesn't explain why the amplitude of, well, what I've called A here, which in the interests of clarity, I should probably have called J0. In some sense, why is J0? Oh, by the way, here the correlations that we match are averaged over individuals. So maybe our analysis here has fallen victim to the problem that we're trying to cure over here. And so at the moment, I would say it's not only because we did it more recently, but I do think I believe more in this than in that, although I think that was worth talking about, because I think the idea of trying to build explicit models is a good one. It just faces problems. Okay, shall we talk a little bit about embryos? So, what's the problem? The problem is The problem is the following. I've told you that in the development of the fruit fly larva, right, the development of the embryo leading to the larva that crawls away, you build a segmented body plan. The number of segments is always the same, but the size of the organism will vary. By the way, not by a lot if you have genetically identical organisms, but if you ask the same mother to lay lots of eggs, they'll fluctuate in length by the standard deviation of 4%. So that means that if you collect hundreds of embryos, you can see things that are plus or minus 10%, so 20% apart. And if you think about it, since, well, there's a question of how you decide how many segments there are. If you think about those genes whose pattern of expression as a function of position have 7 peaks, if I can find embryos that differ in length by 20%, first of all, I have enough space to squeeze. If you thought that what you were doing was producing something periodic, you have enough space to put in an extra one, and that never happens. Also, you have enough variation that if you think about the absolute distance from the head to stripe N, if you look in the longest embryo, that distance will be farther than the distance to stripe N+1 in the shortest embryo. So they kind of are passing each other, right? So either the thing scales and gets rid of the length variations, or there's something weird going on that maybe we just haven't seen it. So lots of people had thought about this, and my colleagues and I went back, and it's a long, complicated story. We had an undergraduate who worked with us, Mariela Petkova, who did spectacular versions of these experiments with the fluorescent stainings, measuring the spatial profiles of many different genes, some simultaneously, and so on. And when we got to thinking about this, we were joined by a postdoc, Milos Nikolic, who realized that he could sort of sift through all of the data she had collected, and that there really were hundreds of embryos, and everything was calibrated well enough that you could actually merge the data. So it's a kind of, by the way, all these data were collected more than 10 years ago. So it's not that there's some great state-of-the-art thing that just happened. It's rather that we finally managed to take advantage of the patience and care of one experimentalist working very hard with classical techniques. Okay, so first problem. Remember I told you that you can measure time during the 14th nuclear cycle by looking at the progress of this invagination membrane that eventually separates the cells. If you do that, you find that all of these stripes move as a function of time very systematically. They drift linearly. So the first thing you need to do in order to compare across lots of embryos is to correct for that, right? Because otherwise, you're conflating a systematic variation in time with something that might be a failure to scale or just plain noise. So first, get rid of that. And then, sure enough, if you measure the absolute position of a stripe versus the length of the embryo, of course, you don't have embryos of length 0, but you do have lots of embryos that are out here. And the absolute position, right, this is in microns, the absolute position of the stripe is proportional to the length of the embryo, and the jitter around this is the 1% jitter that I talked about yesterday. And that's true not just for one stripe, but for all 7, and you can do this for 3 different genes, and it all works. Let me point out, by the way, that we used to say that since the precision is 1% and the fluctuations in the length of the embryo are 4%, obviously it has to scale, because if you didn't scale, you'd have 4% errors. Well, you'd have 4% errors if you were at a fixed distance from the head, and that distance was very close to the tail, then indeed you would fluctuate by 4%. But if you were 1/4 of the way, then you'd only fluctuate by 1%. So in fact, if you think about it, your error in fractional position, sorry, maybe the better way to do this is to be more explicit. So this is the standard deviation of my distance measured in fractional units, averaged over all the embryos, which of course have different lengths. And so what we see is a line at 0.01. And that's true when from x over L is 0 to x over L is 1. And of course, we don't have points everywhere, but we have 27 points that are scattered across the length 21, right? 7 stripes times 3 genes. So then you say, well, suppose that every stripe was anchored to the head in absolute distance. How much variance in fractional distance would you get? And the answer, of course, is that if on average you're at the head, it doesn't matter where the tail is. And so you could get a standard deviation which was 0, but the further away you went, the larger the apparent variance would be, until when you were finally out here, you'd be at 4%, right? Which is somewhere 1, 2, 3, somewhere up here, right? So actually, I didn't do so badly. But then you could say, well, that's stupid. If I don't know how to scale, the least I should do is anchor myself to the nearest thing. So some of the stripes in the back should be anchored to the tail. But now I have 2 signals. I have one signal that says how far I am from the head, and another one says that how far I am from the tail. I could combine them, and if you combine signals, you sum 1 over the squares of the variances, and right, the usual thing. And so what you get is this. And the evidence for scaling is this. It's the fact that this level is below that, which is a much smaller effect than you might have thought. And the only reason that you can see it is because A, the scaling itself is so precise. So you could scale on average, but be noisy about it. And then in that case, you wouldn't actually have enough length variation in the natural population of embryos to tell that you're scaling. To be sure, anyway. And you have to have enough data that, since you're estimating a variance, of course, your fractional error is related to the size of your data set. So you have to have enough data that you can push the error bars on these quantities down so that this difference is significant, and it's massively significant. So we think this is sort of direct evidence for scaling in the stripes. But you know that the stripes are driven by the gap genes, which have these patterns of spatial expression that look like this, and there are 4 of them, so I'm not going to draw all of them. And there's noise, and the noises are correlated. And so for those of you who saw the colloquium yesterday, we can measure all this stuff, right? Now, how do I decide whether this pattern is scaling or not? So you could say, well, it's simple, right? Look at the patterns, ask whether when you plot them as a function of x over L, they fall on top of each other better than if you plot them as a function of x. Well, first of all, we have this problem that you don't know whether you're anchored to the head or the tail. And second of all, when you say fall on top of each other, remember that they are intrinsically noisy. Not very noisy, but a little bit noisy. So you have to have a way of comparing how similar they are in units of their own noise. So the way to do that is to ask about information. So if you know the concentrations of all these proteins, then that gives you a certain amount of information both about your absolute position and about the length of the embryo. Right? Because those are the only 2 things you could learn about. So you could say, I saw, G1 equals 0.7, G2 equals 0.3, G3 is 0.01, G4 is 0.001, and that must mean that I'm 200 microns from the head in an embryo of length 500 microns. Because I measured 4 things, I only need to learn 2, that's possible. And my error bars on those statements are something. But if it scales, then what that means is that really all the information is not about position and length, it's only about the ratio. And so to be more precise, what you would say is that the information that you have about where you are and how long the embryo is can be decomposed into a part that is information about your scaled position and something extra. Right? And how you choose to interpret that is up to you. But importantly, this decomposition is unique. And so what you do is you sit down and you write down all the probability distributions and you do a little bit of algebra and you figure out what am I supposed to compute from the data that allows me to estimate delta I. And if you think about it, this is the entropy of the probability distribution of x given the GI, of x over L given GI, minus the entropy of the probability distribution of x over L given GI, computed only for embryos of length L and then averaged. Right? So the entropy of the distribution measures my uncertainty about the thing that I'm estimating. So what I could say is I look at the gene expression levels, I have an estimate of where I am in fractional coordinates. That estimate has an uncertainty that's quantified by computing the entropy of the distribution. And I'll remind you that if the distribution is Gaussian, then this entropy is related to the determinant of the covariance matrix. So there's a concrete path for computing it, right? On the other hand, if I sort the embryos into classes depending on how long they are, and the entropy is significantly smaller, then that must mean that there was also information conveyed about how long the embryo is, right? And that somehow it doesn't neatly decompose into all being information about fractional position. So I told you the distributions are a Gaussian to a good approximation, so we can reduce this to the problem of computing determinants of covariance matrices. I will also remind you that even with hundreds of samples, a 4x4 covariance matrix is not perfectly determined. And so the random errors in estimating the elements of the covariance matrix become systematic errors in your estimate of its determinant, right? Because it determines nonlinear combinations, so the errors don't average away. So that means that if you just do this naively, you will get a non-zero answer, even if it's really supposed to be zero. So what do? You change the size of your data set. Now, obviously, you have only as many samples as your experimentalist friends gave you, but you don't have to use all of them. You can use half. And if the reason this is non-zero is because of these effects of finite sampling, then that'll get bigger when you only use half. And you can work out the theory and show that you are overestimating this quantity by an amount which is proportional to 1 over the number of samples. So plot as a function of the number of samples and see whether you see the 1 over n behavior, and if you do, you can feel comfortable extrapolating to n goes to infinity. And then the answer is that this is 0 with 2% accuracy. So that tells you that with 2% accuracy, 2% of the absolute magnitude. Sorry, same lie. Right, I mean, if I told you that it was only so many bits, if I told you the error bar was so many bits, you don't know whether that's big or small. What's important is that it's only 2% of the, so the information that gene expression patterns carry about position, more than 98% of it is information about scaled position. So it really is scaling, as far as we can tell. By the way, you'll remember, so we have evidence for scaling of the stripes. We have evidence for scaling in the gap genes. The maternal inputs do not scale. So scaling is an emergent property of the network of interacting gap genes. So what I want to do with the last few minutes is to tell you something about what that means theoretically. And so to do that, what I'm going to do is something which I have largely resisted doing all week, which is to write down a model for what might actually be going on. And I hope you understand why I've resisted doing that for most of the week. I also hope you'll realize why it's useful here. And so we're going to make lots of simplifications. We're going to say that there are these 4 genes that have concentration G each, and we're going to pretend that that position is continuous, so we don't worry about discrete cells. So if I want to write down a dynamics, I remember that each of them I'm also going to think in 1 dimension to make things simple. I know that they can all diffuse. I know that if nothing else happens, presumably the molecules will be degraded at some lifetime tau. And I know that they are being synthesized at some rate which has a maximum. And let me not worry for the moment about inputs. Let me just think about the dynamics of the network itself. The rate at which the proteins are being synthesized depends on the concentrations of the other proteins, because they bind to the DNA and turn gene expression on and off and so on. And so let me say that I'm interested in steady state patterns. And I'm going to insist that this steady state pattern is really a function of the length of the fractional distance in the embryo. You might ask yourself, where does the length of the embryo appear? And the answer is it appears in the boundary conditions, right? If the derivative were non-zero, then there would be a diffusive flux pointing into the wall. And it doesn't have, I mean, it might be that there's a source of the molecules there, and for one of them, not these four, but for one of the maternal inputs, we know there is. But if you're just thinking about a network that's sort of closed on itself, then there are no flux boundary conditions at the ends. And that's the only way that the network has of knowing how long the embryo is. Okay? So let me emphasize that in order for the pattern in the middle of the embryo to exhibit scaling, the effect of the boundary condition has to be able to propagate in. So what does this mean? If you go to steady state, let's see, there's the natural quantity lambda squared, which is d times tau, and there's also a quantity r max tau, and I can choose my units of g so that that's 1, right? Because if I multiply through by tau, then I get d tau. I've set the left-hand side to 0. I get r max times tau. But if I divide through by r max tau to normalize g, I can get rid of it, right? So what that means is that lambda squared times the second derivative minus 1 plus, sorry, so that's the condition. And this has to be true for all L. And L is hiding, right? And so on. So if it's true for all L, in particular, I can take the derivative with respect to L. And if I take the derivative of this expression with respect to L, well, alternatively, maybe a useful way of thinking about it is that phi I of x over L goes into phi I of x over L minus x delta L over L squared times phi I prime of x over L, right? That's the change that you get in the function if you make a small change delta L. Then when I make this transformation, the equation has to still be true. And the only way that's possible, right, is if you think about taking the derivative of the equation, that's saying that lambda squared times the second derivative with respect to x minus 1 plus, and this is delta ij plus the derivative of fi with respect to phi j, all acting on this change, which is x phi j prime over L squared times delta L has to be 0, right? Where I use a sum on j. So this is just saying that I want the steady state equation to be true, and I want it to be true even if I change L. So let me I don't know how to do that globally, but I know how to take a derivative, so I can take a derivative. So what does that mean? It means that I have some linear operator, ij, right? And that linear operator has an eigenvector with 0 eigenvalue, right? It's a linear operator, so I can always, I mean, unless there's something terrible going on, I can always think about its eigenvectors and eigenvectors and eigenvalues, or eigenfunctions and eigenvalues. it has a 0 eigenvalue. Suppose that I go back to my original equation and I say that GI is the steady state solution. So by steady state pattern, I mean this GI bar, plus a little bit. And let me linearize this equation around the steady state. That linearized equation, of course, also is characterized, I mean, it's linearized, so there's a linear operator that governs the dynamics of relaxation toward the steady state. It's the same linear operator. So what that tells you is that scale invariance in steady state implies a 0 mode in the dynamics. So there's a way of deforming spatial pattern of expression that to leading order doesn't relax. Or alternatively, if you abuse your dynamical systems concepts a little bit, what you can say is that all the modes of deforming the pattern have a kind of stiffness that's pulling them back toward the true steady state. And the relaxation rate is proportional to that stiffness. But if there's a 0 mode, it means that there's a direction of deformation of the pattern which has no stiffness. And then you realize, of course, it's the one where you dilate the pattern, right? Because it's scale invariant. So first of all, I find it interesting that by thinking about spatial scale invariance and making the approximation that you're in steady state, you can draw a conclusion about the dynamics. Also, most networks don't have 0 modes. So there must be something special that makes this possible. And the way to think about this, then, is that somehow this complicated the structure, and this is the only place where there's real structure in the network, right? The network has a structure such that in the interior of the embryo, there's actually a 1-parameter family of solutions that are nearly, maybe they're not all exactly solutions, they're very close to being solutions. And all of them are possible, and then you get pinned to one of them by the boundary conditions. And what I want to end with is to point out that this idea of 0 modes comes up in a very different context, which is in thinking about short-term memory in networks of neurons. So if you want to remember a discrete thing, then what Hopfield taught us is the way to do that is to make sure that the network has an attractor whose pattern of activity represents the thing you're trying to measure, so you'll relax back to it. But what if the thing you're trying to remember is a continuous variable? Well, if you generalize this, what this must mean is that there's a line of attractors, and you can stop anywhere. And if I put you at one point, well, you might diffuse a little bit, but you don't systematically drift. And that model sort of came out of thinking about a very practical problem, which is how you hold your eyes still. Sorry, I have to tell you about this because it's a surprising connection, okay? I think you all know that, right, if you rotate your head, you counter-rotate your eyes so that the world doesn't seem to move, right? Now, when you do that with your eyes open, you could say, well, that's not surprising. I'm looking at you. I can turn my head and keep looking at you. That's not hard. The surprising thing is that if you close, I put you on a rotating chair, and I turn the chair, you still counter-rotate your eyes. And the reason is that you have your semicircular canals in your vestibular system that tell you about the rotation of your head. The trick is that your semicircular canals are motion sensors. In fact, they're inertial sensors, but because there's viscosity, they become velocity sensors. And so that means that it can tell you about the velocity at which you're rotating. But that's not enough, because after I rotate you, you hold your eyes counter-rotated, and you do that for half a minute. During that half a minute, you have to be contracting the muscles of your eyes by the correct amount to hold the eye in place. That means you have to hold a memory for the integral of the velocity signal. So in 1996, Sebastian Sung wrote a beautiful paper in which he pointed out that if you have one of these line attractors and the vestibular signals can provide you, and the line represents position, then if I push you, if I push you along the line by moving and then stop pushing, you'll stay put because it's a line attractor. And he also discussed what features of the dynamics of the underlying neural network are necessary in order to make that be true. And there's an enormous amount of data showing that in outline this is correct. In particular, you realize that this is you're poised on the threshold of instability. If you think about a linear dynamical system, what you're saying is that one of the eigenvalues for the linear response of the dynamical system has gone to 0. If it crossed to the other side, it would be unstable. So the network has to be tuned to this point, which is a kind of critical point, although that wasn't the language that he used. And you can show experimentally that that happens if you do the experiment in goldfish, you build a kind of virtual reality setup for goldfish so that you can adjust how much the world rotates when they rotate their eyes. And if you give them more gain, then they tune the network in one direction, and if you give them less gain, they tune the network in the other direction, and then you take away your feedback loop, and either you've trained the goldfish so that its eyes are constantly going like this and it's unstable, or that they try to move to something and then they always relax back. And the training happens on the scale of an hour. So a class of neural networks that hold the memory of continuous variables have 0 modes. We know that those are maintained by learning. What we find here is that in order to have spatial scale invariance, the dynamics of the underlying network for this network of interacting genes has to have a 0 mode. But I don't have any learning, so I don't know how it arrives at this. So I'll stop there.
Questions?
Thanks, Bill. That's beautiful. If we think about this synaptic analog zero mode that you mentioned, we could, in principle, come up with strategies to play with it and see whether this thing is disturbed by whatever means. Can you think of something that could be done there to try to probe that or disturb that or somehow interfere with that? So, I mean, is there something to gain if we could?
So the thing is, you would like to make a quantitative rather than a qualitative change, right? Because if I knock something out and things fail to scale, it could be because of this, and I've disturbed the structure of this linear operator, and so now, right, so I have this, in my theory, if I cross out an arrow in the network, then I'll push this away from having a 0 mode, and so it won't scale. But what the experiment was, I made a mutant and it stopped scaling, and I'm sure that biologists will have some other explanation for why that was true. The cool thing about the neural example is that you can make a quantitative change, right? When I change the gain between eye movements and world movements, I have a continuous dial that I can construct. The closest, the place where you want to get, the direction that people are going in, I mean, not just for this, but generally for these kinds of problems, is to have optogenetic versions of the proteins that you're interested in. So what that means, for example, is that you've got a gene that encodes the protein that you're interested in, but somehow it's not functional until it absorbs a photon. Now, that can be reversible, irreversible. There's a variety of ways of doing it. And some of the molecules in the fruit fly, there are now versions of those, but none of them are yet quantitative enough to touch these questions. I should point out, by the way, that if you have zero modes, you should have other things. Like, you should maybe be able to see that as the pattern is changing, some combinations of genes are changing slowly and other combinations of genes are changing quickly, right? So, you know, it's not really clear that you're in steady state, but as you approach this, what we're going to call the final pattern, you know, 45 minutes into nuclear cycle 14, you see that some combinations of genes are varying fast and some of them are varying slow. And you also see these long-range spatial correlations, which I talked about in the colloquium yesterday, which are another consequence of having zero modes, right? Because if I have zero modes, they're spatially extended. And although I don't have noise in the model, if I add any reasonable source of noise, I'll drive the zero mode a lot, and that will produce long-range correlations. So there are lots of things that are consistent, but we don't have quantitative relationships between them yet, and we don't have the direct perturbation experiment. The quantitative relations, if we think harder about the theory, we might actually be able to get there. But
thank you, Bill. I do have two questions. One of them, I don't know if I'll be able to articulate properly. I will start with the easier one. On the first part of the talk, the scaling law implies on the coexistence of multiple time scales.
mm-hmm.
So did you attempt to do any recovering of the time scales? I don't know, maybe doing inverse Laplace transform or something else?
So you can do something much simpler, which is to say, assume that the correlation function is a sum of exponentials and fit the data. And that was why I said you can do it with, you can get within the error bars with 6 exponentials, but then you have to, first of all, they have to be rather precisely equally spaced, and more dramatically, the amplitudes of each one have to be adjusted to get to within the error bars. They have to be adjusted in relation to the time scale with an accuracy of a few percent. So I would say that, of course, I can rewrite anything. As you say, take the Laplace transform. You've taken any function and rewritten it as a sum of exponentials. You say, well, in principle, it's an integral over exponentials, but the data are finite, so probably I don't need the integral. I can get away with a sum. And so why are you so impressed? And correct. That's all correct, except that it turns out that if you want to follow that path, you've just pushed the problem somewhere else. You have to explain why the amplitude of the component on timescale tau is exactly 2 to the 0.36 times as large as the component at timescale 2 tau.
Okay, thank you. And the second one is, because the maternal proteins, they won't scale with the size of the embryo. So what I was wondering is, when there is not a scaling, because some of them are diffusing, they will fall exponentially with the space. So they will cause a fluctuation in a given position. So the readout, when the cell is going to read that concentration, it should have sort of lie within the condition that the cell would still be able to recognize the maternal input at that position. So what I'm trying to say is, did you attempt to measure how much information you are losing when there is this change in size, so that still the 4 transcription factors would still be enough for the cell recognizing its position along the embryo?
So, good. Okay. So first of all, the maternal input where we can make the best measurement is the one that's high at the head, as you know, but maybe not everybody else knows. And as far as we know, that's not regulated. So if you wrote an equation for it, you wouldn't have this term. You would have diffusion and degradation and the boundary condition, which is a source provided by the mother, and so then you get a length scale and you're done. There's no way to get around that. It seems. I mean, we didn't discover that, right? That's what everybody thought, and we haven't seen anything that's inconsistent with it. If I look at the whole network, there's the possibility of, despite the fact that there's a length scale here, I still end up with a 0 mode, and then I become scale invariant. So in some way, this framework doesn't explain how you take non-scale invariant inputs and generate scale invariant outputs, but it does explain why the inputs can't be scale invariant, and that it has to be an emergent property of the network, because that's the only way to get rid of this length scale, at least local. I mean, I did this by taking a derivative, right? So I don't know that it's true globally for all L, but that's okay because L only fluctuates by 4 or 5%. But still, that's enough to show that it's scaling. So I get a kind of local scaling. In terms of, how this, it feels like in this process of taking a non-scale invariant input and generating scale invariant outputs, I should lose information somewhere. No, whether that's correct. What I know is that we've always measured the what I know is that the information that these molecules convey is, to a very good approximation, only about scaled position. So whatever non-scale invariance came from the input, that has been forgotten. So in some way, there might be a way of doing this where because your dynamics has scale invariance, I somehow project out the components of my inputs that are not scale invariant, but I don't actually know how to turn those words into equations. Yeah.
Thank you for the lecture. My brain is really numb right now.
I'm not sure whether that's a good thing, but go ahead.
That is a good thing.
I'll take it as it is. We can discuss later.
Yeah. So I have a doubt about the third.
Yeah.
The third blackboard.
Yes.
Yes. So this graph you drew with the pointed lines.
Here.
Yes. Why? So the points below this yellow curve are
That's data.
That's data, yeah. And it's evidence for scale invariance.
Because it falls below the yellow curve. So there's no way the dashed line, the yellow one is a little bit of imagination, but the dashed lines are straightforward. That basically says if I'm anchored to one end or the other in absolute coordinates, then I will appear to fluctuate in scaled coordinates because the length of the embryo is varying. And this is the magnitude of those fluctuations, right? If I'm anchored to the head and I'm at the head, it doesn't matter where the tail is. I'm still in fractional position, I'm still 0. But if I go out to position 0.1, 10% of the way, if I'm anchored in absolute position, then I will fluctuate by 0.4%, right? Because the length is fluctuating by 4%, and I'm normalizing by that, and I'm 10% of the way. Right? So the amount by which I fluctuate is my fractional distance times the fractional fluctuation. And so this is a number like 0.04, and then this is whatever it is. So the surprise is not that something that's very close to the head scales, because in some sense it doesn't need to, right? Your fluctuations in fractional coordinates will be very small, not because you've compensated, but because you have this factor working in your favor. But by the time you get to the middle, you have a problem. Then you could say, well, but wait a minute, the middle is special, because I can think of ways of finding the middle that don't give me a continuously graded signal. And so that's why having a whole segment of things that are below these bounds feels significant. I mean, you could also say that when you look at these plots, you can stop. But it is interesting, it's a little bit more subtle than that, I think. But
oh yeah, and now I understood the significance. Thank you.
sure.
You did a partial differential equation for one species, but if you add...
Well, I cheated, right? It would have been better if I cheated more explicitly. I wrote for each species that it diffuses and degraded and is synthesized at a rate that depends on the concentrations of all the other species. Actually, including yourself, at least in principle. And in practice, by the way, there are auto-regulatory loops in the circuit.
Any more questions? Okay, then
Okay,
let's thank Bingle again and meet at 2. Okay. So I'm not sure there's something in the like here after, but just to be sure, make sure that you don't leave your stuff here after 2.